Swayam Prabha. Digital India. Educated India.
So now I am going to talk about some theory, right. So I am going to define what my what would I call some safe set or forward invariant set, yeah, and this is defined as C equal to, say, suppose I define my set using some notice that I have defined it the other way around, right. Here if you see my, no, I think this is fine, right. I have also defined it using 25 minus x1 square greater than equal to 0, 9 minus x2 square greater than equal to 0, same thing. H can be an amalgamation of 25 minus x1 square, 9 minus x2 square, right, same thing, that is the set C. The boundary, like I said, is basically where Hx is exactly equal to 0, and then I have C naught. I would say the interior of C is the set of x in Rn strictly greater than 0. Okay, great. Now, so typically if you see the way we have been defining these is that we have sort of, I mean, yeah, that is fine, I mean, in particular cases. So the reciprocal barrier function, that is what we have just looked at, is basically something like, say, Bx is equal to something like, I guess, 1 over Hx, right. This is how we have been using it, right. It is like 1 over 25 minus x1 square or 1 over 9 minus x2 square. Okay, this is how we have been doing, right. And what we the condition we sort of imposed was that B dot is less than equal to 0. Okay, this is the sort of condition we were imposing. However, we do not need this, means it is too restrictive. Yeah, it can be shown that this is again going back to the same idea that everything inside is also being made invariant in some sense. Okay, so we do not particularly need this, alright. So if you go back to our example also, again if you go back here, if you even in this example, what did we do? We said that V dot is less than equal to 0, same thing that we do with our typical Lyapunov analysis, right. Not exactly the barrier function, but the Lyapunov analysis, right. So what does this mean? This means that this set is a square, right. So if I start inside this square, right, if I started close to the boundary, okay, what will it do? It will make some kind of a set, right. This V is now complicated, by the way, I can't really make a shape out of it, but this V is complicated. What it will do is it will make a set which is something like this, say, for example. We will try to get close to a continuous version of a square basically, if you started here somewhere, right. But if you started smaller, it will make a smaller square, right, because that is how the invariant set for the V dot less than equal to 0 works, right. We already saw this. If you start in the inside ellipse, you will remain inside the inside ellipse only, right. You do not have to actually, let me think about it. In this case, would it be true? Actually, it is not very clear if that will be true in this case. Does it mean that the inside set actually depends on how the shape is? Actually, I am not sure, honestly speaking, yeah, because I have to see the shape, and this will be a good exercise to see what is the shape of the level sets, that is V equal to constant, what is the shape that you get here. Okay, it is not very obvious to me what the shape will be, yeah. Yeah, I don't think it's because this is looking like what this is this, can I write this as 25 minus x1 square divided by yeah, I can write this as 25 minus x1 square divided by this. So this becomes 25 divided by 25 minus x1 squared minus 1, and similarly for the other one this becomes 25 over 25 minus x1 squared minus 1, this becomes 9 over 9 minus x2 squared minus 1, right. So it is actually some kind of an ellipse only, right, some funny kind of a, is it still, no, it's not an ellipse, right. Yeah, it's not very clear what the shape will be, yeah, but the sort of point that I am trying to make is, as you keep reducing your initial conditions, you will get smaller and smaller sets, that is the hope, I guess, right. You will start getting smaller and smaller sets, and the smaller set will become invariant. You will not end up exploring the larger set at all because of this condition, okay, and this is a little bit restrictive again. And this happened why? Because we took v dot less than equal to 0, this kind of a condition is what we used, right. So that is apparently not required, this is what some of the research has been. Apparently all you need is, this is what is the relaxation, is that b dot is less than equal to gamma over b, where I guess gamma is some positive constant, okay, gamma is some positive constant. I hope you sort of understand what this equation is doing, okay. What is it doing? It's saying that if you are very far from the boundary, okay, if you are very far from the boundary, what happens to b? Typically, I mean, if you look at our barrier function, b is some finite value, okay, it will give you some, you know, finite sort of decay, yeah, hopefully it will give you a finite decay, I guess. Let us see, if I look at this barrier 1 over hx type of case, so in our case we are looking at what, yeah, I am trying to sort of make sense of how this will look for us. Let us see, suppose, let us look at our example, okay. So in our case bx was 1 over 25 minus x1 squared, okay. So unfortunately this may not satisfy this condition, which is why I am not very sure. Okay, let us see, what is b dot of x? This is 2x1 x1 dot divided by 25 minus x1 squared whole squared, correct, thank you, right, yeah, no minus, it is a plus, that is fine, okay, that is fine. But this is not going to be very obvious how we are doing it, no, this is not very evident. But the rationale for doing this is, at least how it is stated here, is that the inequality allows for b dot to grow when solutions are far from the boundary, okay, yeah. So basically what this will do is that if x is far from delta c in c naught, then obviously your b is positive, right, because of whatever, how you have constructed it, right? B is going to be positive, so there is going to be some positive quantity on the right hand side, right? B is positive, right, because I took 1 over hx and h is positive in the interior, right, h is positive in the interior, in fact it will be more and more positive in the interior, right, as you go further in the interior it is more and more positive, okay, that is the definition of the set, right. So obviously h is positive, 1 over h is also positive, okay, that is the idea. So if you are in the interior, if you start in the interior, your b is going to be positive, and so this is right hand side is going to be positive, okay. So what am I saying? That the derivative is less than some positive number, okay. So basically b can increase okay, because all I am saying is that derivative is less than a positive number, so it can also be positive. So this allows for b to increase. What does the increase of b mean? Remember, b becomes infinity at the boundary for this reciprocal type construction, right? This becomes infinity at the boundary. So b increasing means you are going closer to the boundary, okay, makes sense. So b can increase implies x moves towards delta c. This is allowed by this construction, okay. So this was, so by this is allowed only in this construction. If b dot was less than equal to 0, this is not allowed, because it is always going down or not reducing, or it's never increasing. B dot less than equal to 0 means b is never increasing. Here there is a possibility that b can increase. However, what happens when you go close to the boundary? If x near delta c implies b is large, right? That's how we have defined it. You remember 1 over 25 minus x1 squared. If x1 reaches 25, the denominator is exploding, the denominator is going to 0, so b is becoming large, okay, alright. If b becomes very large, what happens to this guy? Almost 0, almost 0. So therefore b dot implies b dot approximately less than equal to 0. So b either does not increase or starts to decrease, okay. So what is it saying? It's saying basically only this boundary h of x is in effect. The inside boundaries are not, like in this case I could have remained inside, right, I could have remained inside this and not even gotten here. That is not allowed here, yeah. Here the right hand side is positive for some time, you are allowing some growth inside the set, okay. But as you start getting closer to the boundary of the set, this growth stops, okay, this growth stops, okay, which means implies x cannot escape c, yeah. And this is not difficult to show. I mean, these folks have actually shown it. So basically how they are saying it is that, so this is the b dot, so what is b dot? B dot is equal to minus 1 over hx squared times h dot, and if this is less than equal to gamma over b, this is gamma h, right. So this condition means that h dot plus gamma h cubed greater than equal to 0, yeah, this is what you will get. So what did I do to get this? I think it's evident, right. B is defined as 1 over hx, right. So b dot is this guy, correct? I think I did it correctly, you can verify. B dot is minus 1 over hx h dot, hx square h dot, and the right hand side is gamma over b, and that is this guy, yeah, which is gamma times h, right. So that gives me this kind of a differential inequality, yeah. This can be solved, yeah, using your comparison lemma type results, and they have actually solved it. I am going to just write it. Hx tx0 is greater than equal to 1 over square root 2 gamma t plus 1 over h squared at x0, okay. Okay, so you get this basically just by solving this with initial conditions on x and all that, not difficult, right? You can just solve this equation, yeah. This is a differential inequality. You can just solve the equality and then by the comparison lemma make it greater than equal to, done. So you will get this solution, yeah. Please verify this. I am also not sure, but it's not difficult to see that this is already giving me h greater than equal to 0, right. Right hand side is positive. Yeah, right hand side is positive, not a negative quantity, right? So this is, you are always getting some positive number on the right hand side, which means what? You are inside C, right, for all time, right? So this implies what? C is forward invariant. Okay. So this kind of barrier function already did something better than what we did by making b dot is less than equal to gamma or b. Of course, you have to be careful how to choose this b and all, and how to make it, and so those things are not obvious here. Yeah, unfortunately, I am not sure we will have time to discuss those, but this is how you define a barrier function. Okay, this is the right way, that you want this to happen. Okay, not less than equal to 0. Yeah, that is just too much to ask. Yeah. If you can enforce this via the control design, excellent. It would be the best way to go, that this happens. Okay. Now, one final notion, yeah, that I sort of want to talk about is basically the notion of which is slightly more than this. It is zeroing. Yeah, just a second. Yeah. Which? This? Why? Why are you saying it's negative? T is positive, no? No, it's the positive square root. No, don't worry about that. It's always the positive square root. You can verify in the solutions. Yeah, okay. I mean, it's a, see, the basic idea is the continuous, the solution is continuous, right? Yeah. So either you are always positive or always negative. Okay. And at initial time, if you are positive, there is no point in taking the negative square root. No, the solutions are continuous, so you will always work with one side only. Yeah. Okay. All right. Zeroing barrier functions. Okay, this is what is a little bit more advanced, right? Not much. Okay. So sort of the final notion. I'll sort of take a few more minutes and we'll be done. Yeah. Here, even in the previous case, if you see, your function still became infinity on the boundaries. So you can imagine, whatever you do, whatever these tricks you do to make sure that the inside set does not become invariant and all that, great, that works, but your control might still go unbounded if you start close to the boundary, because that's a feature of how you've defined it, just like here, right? Control contained this guy. You start close to the boundary, same deal even there, because that's how you defined your barrier function, 1 over hx. Okay. So this is one unseemly thing that you want to avoid. You don't want the control to explode as you start close to the boundary, right? So that is where the zeroing barrier functions sort of come in. They are defined in a slightly different way. Let's see. I'll talk about it. First, we define the notion of a extended class K function. You already know what is a class K function, because it's 0 at 0 and strictly increasing. But the arguments are always taken to be, argument of a class K function is also taken to be positive. Whenever you define a class K function alpha, you say that it goes from R plus to R or whatever. Right? Now we don't do that. Now it's allowed to go from R to R. Okay. So this is basically the notion of an extended class K. So alpha 0 is 0 and alpha strictly increasing. Basically negative arguments are allowed. Okay, negative arguments are allowed. That's the idea. It is not necessary that the argument must be positive, because if you remember, we always take this class K function as norm of x and norm of x squared, and which is basically argument is the norm. Right? So the arguments were positive. Here the arguments don't have to be positive. Okay. So basically negative argument allowed. That is the whole point, because once you start at 0, of course it is going to be positive for values greater than 0 of the argument, but values less than 0, no, right. So that is the important thing. So this is why it is sort of this is the sort of extension of, if you remember, Lyapunov functions are always positive definite, and how was positive definiteness defined? By comparing it with a class K function, right. Now we compare this barrier functions with a extended class K function, okay. This gives us flexibility on both sides, right. There it was, the function was always positive, so the Lyapunov candidate was of course always positive. Here the function can also be negative, so therefore this function can also go negative. That is the whole point here, alright. Okay. So suppose you have again a definition, so zeroing ZBF is the zeroing barrier function. How do we define it? Yeah. So this is H belongs to C1 is a ZBF for set C. Yeah, we have defined the set C, the safe set, right. If there exists extended class K function alpha and set D with C being a subset of D being a subset of Rn, such that for all x in D, LFH x is greater than equal to minus alpha Hx. Okay. Yeah. So remember, dynamics, we were looking only at a dynamical system, there is no control, therefore only LFH, no LG and all that. Huh? So LFH is what? Just H dot, right? It is just H dot in the along the trajectories of the system. Huh? So this is the direction derivative. So what am I saying? I am just saying that there is a larger domain, of course, the C has to be part of a larger domain, and in that larger domain this H dot must be greater than or equal to minus alpha H, right. Now the one of the simplest, so now notice that H itself, the way we have defined C, notice, yeah, we have defined C, H is not stopped from being negative, right. In this definition it does not say H cannot be negative or anything like that, right. H can be negative, right. It is all we are saying is that whenever it is greater than or equal to 0, it is the set C, right. Otherwise outside the set C, H is potentially negative, right, because whenever it is positive it is in the set C, right. So whenever you are outside, just like here in these examples, I mean I guess you can see this example itself, right. When H is positive, x1 is less than 5 plus minus 5, x1 is between plus minus 5. If H is negative, it is outside, okay. So H negative is allowed, no problem, yeah, okay, great. Now what do we want? We want H dot to be equal to greater than or equal to minus alpha H. So this is basically a or a simplification, or actually this is a generalization that way. This is a generalization of what? If you take alpha, there is this extended class K function as H itself, alpha of H is just H, yeah, because it will be 0 at 0 and then increasing, on the negative side it will go down, no problem, straight line, basically it is a straight line, yeah. So if alpha function is taken as the unit function itself, then this is the generalization of this guy. So what does this give me? So what do you want to do? You want to basically maintain h greater than equal to 0. Yeah, I hope that's obvious. Now if I solve this equation, what do I get? Let's look at this equation, because it's solving this one, general one, is difficult. Let's try to solve the simpler one. What is the solution? h of t is, अच्छे से बताओ, पूरा बताओ, tell me everything. E to the power of minus gamma t, let's say initial time is 0, and okay, done. H naught, thank you very much, this is important. H naught. Okay. Now suppose if starting in C, or I should be more precise, if x starting in C, then what do I know? I know that h naught x, or how do I say, h0, h naught, which is defined as h at x0, is definitely greater than 0. I will say interior of C. So h naught is positive, right, because that's how I defined h. Right? So what does this mean? Implies h t is always greater than 0, and h t goes to 0 as t goes to infinity. Okay. Alright. So what's the good thing in this case? In this case, what's the nice thing? Nice thing is that, again, I mean, it should be obvious to you that x of t is also in C. Yeah, also in the interior for all time. Forget infinity, infinity is not in real numbers. So x of t is going to remain in the set C. So this definitely, this method also made it invariant. Okay, but it has a nice structure, right? I mean, it's a nicer structure. There is no reciprocal happening here. There it was h dot is gamma over h. Here it's gamma times h. Okay, so also nice, right? So again, a similar feature that you will see is that here, as you go close to the boundary, h is going to go to 0, going to go towards 0. Right? Therefore, by this law, as you go close to boundary, you will stop moving. Gamma h is close to 0. Stop moving. You stop further increasing or anything. Yeah. If you are far from the boundary, h could have large values. It could have large, but you are inside the set. Suppose you are, of course, if you are inside the set, let's assume you are inside the set, yeah, h is positive, okay, could have large positive values as you go further in and in the set, yeah. So h is decaying, which means it is being pushed towards the boundary. Earlier we were looking at everything in the perspective of 1 over h, therefore we were thinking the other way around. Now it is the other way around. 0 is, h equal to 0 is the boundary. So as you are in the interior, h is large, therefore minus gamma h is large, therefore you can potentially get pushed towards the boundary, right, because h dot equal to minus gamma h is basically going to push you towards the boundary, it is going to reduce h, right, that is fine, you are allowed to explore that region. And as you go close to the boundary, h is going to become 0, you do not further move, you have stopped, okay. So that is the idea, that there is no reciprocal nature here. So when you do a control design with this, we are of course out of time, we will not be able to do a control design and all that, but typically constructing these is not easy, that is the thing. Typically how this is done is, folks usually solve quadratic program, they do not actually, what they do is they do not actually, they only construct the h and they put a quadratic, these are all quadratic program conditions, right. If you see, these are QP type conditions, these are actually QP type, if you do not see also, I am telling you, this is QP type conditions, yeah. This is like the barrier condition, and correspondingly there will be a control condition which is going to make states go to 0. So there will be a control condition, barrier condition, and the two are solved simultaneously using a quadratic program, using some, say I want to minimize control or something like that, okay. And this, so they do not actually solve this by hand analytically. So it is not typically easy to solve all of these by hand, but these reciprocal ones you can see you can do by hand. I would really strongly suggest that for the same sort of example, you try to construct these zeroing barrier functions, okay, also, alright. So, why is it called zeroing barrier function? Because at the boundary we did not do anything. Earlier we took a reciprocal, right, 1 over hx and things like that. Here we took the h itself as the barrier function. H itself is the barrier function, right, and we were just ensuring that the h is such that h dot is greater than or equal to minus alpha h, okay, which means that it has a nice zeroing property. Yeah, the barrier function becomes 0 at the boundary, because the barrier function and this function are kept the same functions, to be honest. Yeah, so the barrier, so that's why it's called a zeroing barrier function. On the other hand, when we took the reciprocal ones, at the boundary they explode, here they become 0, right. So it's like you stop moving at the boundary, right. Therefore we will not need large force to push it back typically, okay, that's the idea. So I would really recommend that for some simple example like I tried, you try to come up with a zeroing barrier function, okay. It's essentially this h of x function such that h dot is greater than or equal to minus alpha h. Can one come up with that? And so if you are looking at the control problem, there is no difference per se, right. It's all these conditions, this condition becomes yeah, exactly the same thing, just with the control, right, and this condition becomes okay. It's just like the CLF conditions, right? This is the conditions, that's all. It's just that you have a control term here to play with. This helps you in the design. In the control case, you have a control term now, and you can play with the control so that with whatever B you have or whatever H you have, with using this control you can get this. That's the whole idea. Yeah, I would strongly recommend you try, because that's what we did, right? We did the control problem. I will post this article and you can take a look. Yeah, they're rather nice articles. The entire field of bipedal robot walking is now relies on this. Okay, this is the Aaron Ames's group, and these guys are pretty much experts at it. Okay, all right. Okay.